Dear students, in this lecture I am going to discuss external characteristic of an alternator. In previous lectures, we have already discussed open circuit characteristic, short circuit characteristic, zero power factor characteristic. So here, under this characteristic, we observe the variation in alternator terminal voltage against armature current. That is, external characteristic shows variation in armature terminal voltage with the variation in armature current for constant field current, speed and power factor. That is, if field excitation is fixed, a speed of the rotor is also fixed, and for a given power factor. So first draw a horizontal line corresponding to no load terminal voltage. When Ia is 0, so EF is equal to no load terminal voltage. So let us take any power factor load. For unity power factor load, during armature reaction lecture we have already seen its effect, that is cross magnetizing. And remember that once Ia current will flow, Ia Ra drop will always be there. So voltage will be down and down with increasing Ia, because Ia Ra drop will increase. Apart from that, the unity power factor load will have cross magnetizing effect. We know it very well in those lectures. So the variation in terminal voltage will be like this. You may write here UPF load, unity power factor load. If our power factor is lagging, then its effect will be mixture of demagnetizing and cross magnetizing. So again it will be like this, down of this curve, decreasing. Let us take any power factor, let us say 0.85 power factor lagging. For further lower power factor lagging, it will be down. Let us say 0.65 power factor lagging. For zero power factor lagging, it will be something still down than these curves. So we may write zero power factor lagging. In zero power factor lagging, we have seen that the armature reaction effect is purely demagnetizing, whereas for unity power factor, cross magnetizing, and in between lagging power factor, mixture of these two, cross magnetizing and demagnetizing, right? We know it very well. For leading power factor, let us take 0.85 power factor leading. So it will be something like this. You may write 0.85. Let us take for representative case, not the exact one, power factor leading. As we know that leading power factor loads are having its effect as cross magnetizing and magnetizing. So magnetizing means it will try to increase the terminal voltage, but at the same time Ia drop will always be there. So initial range of Ia, in initial range of Ia, magnetizing effect dominates the IRA drop, but after that IRA drop dominates. So finally it first increases, then it starts decreasing. If we will have something 0.06 or 65 power factor leading, so it will be something higher than this, 0.65 power factor leading. For 0 power factor leading, it will be still higher, we may write, but it will 0 power factor leading. For higher values of IA, the magnetizing effect will not help, as there is some limit in phi once core is saturated. So further increase in IA will not add its magnetizing effect further once core is saturated. Once phi has reached its maximum limit, that's why it will decrease. After saturation, it will decrease. So with these curves, if you will draw a vertical line corresponding to rated armature current, so you may observe that what is the variation in terminal voltage from no load to full load. So during solving numericals, you might have observed that for the data given for lagging power factor load, full load terminal voltage is lesser than no load terminal voltage. That's why EF minus V upon V is coming out to be positive. But for certain leading power factor load, we may get 0 voltage regulation, right? But we may get the full load terminal voltage higher than no load terminal voltage. Hence, EF minus full load terminal voltage will be negative. Hence, generally for leading power factor loads, voltage regulation is coming out to be negative. Negative means terminal voltage is higher than its no load value. At full load, the terminal voltage is higher than its no load value. So this is the nature shown by an alternator with these conditions. We are not going to change IF, we have fixed it. If we will increase IF, then no load terminal voltage will increase, EF will increase. So that's why we have fixed it. Again, if you will increase or decrease N, so corresponding frequency will be changed and so on. That's why keeping these fixed and power factor also fixed. Suppose sometimes we are fixing at unity power factor, then we are getting this characteristic, this nature. Then again power factor is fixed at certain power factor lag, then we are getting like this, like this. These are certain representative power factors. We may get 0.6, 0. Even 3.5, 0.1 lag, right? 0.995, like that, so on. So here our purpose is just to have an understanding of this nature shown by an alternator. Thank you very much. So with this lecture, our unit 1 is over. Thank you. Thank you all for your patience for attending my lectures.